Good morning. Morning. I'm Farnaz Kadem. I'm Caltech's Chief Communications Officer. I want to thank you all for joining us this morning, and for those of you who are here in the room with us, welcome to Caltech. It's a very special day for us here at Caltech, and we're very happy to celebrate the Nobel Prize winner professors Kip Thorne and Barry Bearish. Yeah, woo! For their decisive contributions to the LIGO detector and the observation of gravitational waves. For today's press conference, I'm joined by Dr. Thomas Rosenbaum, Caltech's president, Dr. Fiona Harrison, chair of the Caltech Division of Physics, Mathematics, and Astronomy, and of course, our newest Nobel laureates, Drs. Kip Thorne and Barry Bearish. Our speakers' full titles can be found in the handouts that you were given when you came in this morning and in the press release that is on our website. Each of our speakers will come to the podium and make some short remarks. They will then take questions from the media present, as well as questions that come into us through email. So please help me in welcoming Dr. Rosenbaum.
Good morning. Welcome to our campus. I'm joined here by Professor Fiona Harrison, chair of the Division of Physics, Mathematics, and Astronomy, David Lee, chair of the Caltech Board of Trustees, in the first row there. And David completed his PhD in physics under the guidance of Professor Kip Thorne. And the two men of the hour, Nobelists Barry Bearish, the Ronald and Maxine Lind Professor of Physics Emeritus, and Kip Thorne, the Richard P. Feynman Professor of Theoretical Physics Emeritus, and Caltech class of 1962. Richard Feynman said of Einstein that he was a giant. His head was in the clouds and his feet were on the ground. But those of us who are not that tall have to choose. LIGO connected the heavens and the earth. Through 4 decades development here on Earth of exquisitely sensitive instrumentation, pushing the capacity of our imaginations, we were able to glimpse cosmic processes that were previously undetectable. It is truly the start of a new era in astrophysics, with the best yet to come. Professors Bearish and Thorne are the 36th and 37th Caltech alumni or faculty members to receive the Nobel Prize. This is an extraordinary number for an institution as tiny as Caltech, only made possible by our culture of ambition and intellectual fearlessness. Caltech thrives on posing fundamental questions and inventing new instruments to answer them. LIGO represents an exhilarating example of how this approach can transform our knowledge of the universe. I will now turn to my colleague, the distinguished astrophysicist Fiona Harrison, who will introduce Professors Bearish and Thorne. Fiona.
So I want to add my congratulations to Ray, Barry, Kip, and to the entire LIGO team. On September 14th of 2015, ripples in the fabric of space-time emitted in the final fraction of a second before 2 black holes merged into one rang through the LIGO detectors in Hanford, Washington, and Livingston, Louisiana. This detection by LIGO of the event was a culmination of many decades of work by more than 1,000 scientists, engineers, and staff. Its detection was the result of one of the most ambitious scientific projects ever undertaken. The ideas for the project go back to the early 1970s, to Ray Weiss's detailed analysis of how one might build an interferometer to detect gravitational radiation, a prediction of Einstein's theory of general relativity. This theory also predicts that any signals would be minute, involving measuring unimaginably small displacements using an instrument built on the unstable Earth. It would be like hearing a tiny bird chirp on the beach against the background of crashing waves. At the same time Ray was imagining this detector, Kip was predicting what sources of gravitational waves might be, the problem being that we didn't know whether these imagined sources would exist in nature. But Kip and Ray persisted in their visions. They joined forces, and Kip recruited Ron Drever to work on the project, and experimentalists with creative ideas for how to improve Ray's design. Ron's ideas proved instrumental in making the interferometer achieve its sensitivity. And unfortunately, Ron passed away this last year after a long illness. But his brother told me that he believes Ron understood what LIGO had accomplished. LIGO was a huge technical and scientific gamble, an instrument nobody knew how to implement to detect sources we didn't know existed. Here, Caltech took a gamble. The administration invested institute resources to get the project off the ground. It was also surely going to be expensive, and three brilliant scientists with absolutely no management experience were at the helm. In 1987, a cosmic ray physicist named Robbie Vogt was finishing his term as Caltech's provost, and at this time, Robbie decided to do something really challenging, which was to become the founding director of LIGO, and Robbie deserves a lot of the credit for getting the project established and convincing the National Science Foundation to make its largest investment ever. Kip's vision for the scientific potential of observing gravitational waves and his ability to share the vision were key throughout. In the New York Times article about the discovery, Kip is described as the evangelist of gravitational waves, which he told me, and modestly, may in fact be his greatest scientific contribution. Kip is a theorist who prefers to work with just a few students and postdocs, and he became one of the founders of what became NSF's largest project. He realized that the quest to detect gravity waves required entering big science mode, and he told me he gritted his teeth and pushed on. LIGO went through many growing pains, and in 1993 it was decided that someone with big project experience was needed to shepherd the construction of the interferometers. Bearish, an eminent Caltech particle physicist who had been a leader of many large collider experiments, got a call from one of my predecessors, Charlie Peck, to convince him to take on the role of leading the construction and implementation of the initial detectors. In addition to rising to this challenge, Barry also crafted modern LIGO's structure and established the LIGO scientific collaboration that has been so important in getting the discovery out and the science. It's for these fundamental contributions that Barry is being recognized today. In 1993, I came to Caltech as a postdoc, and the excitement about the construction of LIGO was palpable, the topic of conversation in many hallways. But there were many skeptics who said LIGO would never work and the resources would be better used elsewhere. However, Caltech persisted and continued to invest in the project. We hired faculty like Rana Adhikari and Yanbai Chen to carry the LIGO vision forward to the advanced LIGO project. Other Caltech faculty joined the effort, like Alan Weinstein, who gave up particle physics to work on LIGO data analysis. Countless graduate students and postdocs also joined the project, drawn in by the vision, but also risking their scientific careers because of the excitement about an effort that many said had no future. For Kip, Ray, and Barry, and all of the scientists, engineers, and staff who have worked on this project, this is your day to celebrate. It is a great way to cap off those many decades of effort, awarded to 3 outstanding scientists, but with thousands of scientists, engineers, and staff sharing in the glory. I will now introduce Kip Thorne.
Go Caltech. So after that introduction, I'd like to evangelize for a few minutes. There are just 2 types of waves that can travel across the universe, bringing us information about the distant universe: electromagnetic waves and gravitational waves. Thus saith the laws of physics. 400 years ago, Galileo created modern electromagnetic astronomy by pointing his small optical telescope at Jupiter and discovering the 4 moons around it, the 4 large moons. We celebrate today the creation of gravitational astronomy 400 years later by LIGO scientists, with our observation of gravitational waves that come from colliding black holes in the very distant universe. Just as electromagnetic astronomy has thrived for 4 centuries, bringing us ever more amazing insights into the universe, so we can expect the same of gravitational astronomy over the coming 4 centuries. The creation of gravitational astronomy is a tremendous achievement, but it's not Ray and Barry and I who really deserve the major credit for this, not at all. The credit goes to the amazing LIGO team of roughly 1,000 scientists and engineers, and especially those in the LIGO laboratory, who designed, built, and perfected the LIGO's detectors, as Barry will describe in his remarks in a few minutes. The gravitational waves that LIGO has discovered are very different from electromagnetic waves. Electromagnetic waves are oscillations of the electric and magnetic fields that travel through space as time passes. Gravitational waves, by contrast, are ripples in the fabric of space and time. They are ripples that stretch and squeeze space and everything that lives in space, such as a LIGO gravitational wave detector. Electromagnetic waves are produced by oscillating electrical charges, matter, real matter. Gravitational waves are produced by oscillating mass or energy, and that mass or energy can be tied up just in the warpage of space and time with no matter present at all, which was the case with colliding black holes. Electromagnetic waves are all too easily absorbed or scattered as they travel across the universe. Gravitational waves are never significantly absorbed or scattered. These huge differences made it clear to me in the 1970s that if the quest to observe gravitational waves could succeed, it could bring a revolution in human understanding of the universe. And that's why I, as a theorist, decided that I and my theory students and postdocs would do everything that we possibly could to help Ray and Ron and their experimental research groups create gravitational astronomy. By 1980, it seemed likely to me that the first thing LIGO would see would be binary black holes. That is, two black holes going around each other that spiral together as they emit gravitational waves, then collide with a huge burst of gravitational waves. Two heavy black holes was what I expected. Why would these be first? Well, the main other possibility was a binary neutron star system. And the distance to which you could see gravitational waves from a binary is approximately proportional to the mass of the binary. And I expected that the black holes that we would see might be 10 times heavier than neutron stars, so you could see 10 times farther. You'd see a volume of the universe 1,000 times bigger. And although we didn't know much about the rates of the number of black hole binaries in the universe, it just seemed to me that factor of 1,000 would overwhelm the lower absolute density of binary black holes compared to neutron stars. And that, in fact, is the way it turned out. And LIGO did see initially the first detections were binary black holes. And that is how it turned out. But there was a surprise. LIGO's first black holes were 20 times heavier than neutron stars, not 10. And astrophysicists are a bit puzzled as to where these heavy black holes are coming from. It's a small mini surprise, and I await expectantly some huge surprises in the coming years. It was also clear by the 1980s that for LIGO to optimally discover waves from black hole binaries and extract their information, it would require comparing the observed wave shapes with the wave shapes predicted by Einstein's relativity. And the only way that we could compute the predicted wave shapes was by solving Einstein's equations on huge computers, so-called numerical relativity. The quest to do these computations on computers had been underway as long as the quest to discover gravitational waves. It's been a half-century quest in both cases. In the early 2000s, I became alarmed that the quest was floundering, so I left day-to-day involvement with LIGO to help create at Caltech a large effort in numerical relativity as an adjunct to the effort that was being led by a former student of mine, Saul Tukulski, at Cornell University. Our combined effort, the so-called SXS collaboration, under Saul's leadership, has produced a computer code that meets LIGO's needs and that underlies the templates that are used to search for gravitational waves for binary black holes in LIGO. I hasten to add that just as I, as a theorist, did not play a significant role in constructing LIGO's gravitational wave detectors, so I didn't play a significant role in constructing the Cornell Caltech computer code. However, I've taken great pleasure in visualizations of colliding black holes that are produced by that code. For the first time, for example, we see through those visualizations the storm in the fabric of space-time that is produced when two black holes collide. The writhing shapes of space around black holes, the wildly oscillating rate of flow of time, the vortices of twisting space fighting with each other in the aftermath of the collisions. There's beautiful agreement between the wave shapes observed by LIGO and those predicted by these simulations. And this agreement makes it clear that the observed waves were indeed produced by a storm in the fabric of space and time. So I'm grateful to Saul Tukulski and the SXF team for their computer simulations. I'm grateful to Ray Weiss and Ron Drever and their students and postdocs for the joys and also, strangely, the tribulations, which I also remember with some pleasure, quite strangely, the tribulations of our collaboration, which led to the concept of LIGO. And I'm particularly grateful to Robbie Vogt, who is here, I'm pleased to see, back in the back, our first LIGO director. Robbie, in the late 1980s and early 90s, forcefully merged the Caltech and MIT experimental efforts, and that was not an easy process, as both of us remember. And he led us in writing a successful NSF proposal to construct LIGO and successful initial congressional funding. He laid the foundations for moving LIGO forward toward construction. And for all this crucial contribution at that crucial stage, I really thank you personally, Robbie. And then I am also grateful and very grateful to Barry Bearish for then taking over, transforming our nascent LIGO project into a form that could succeed spectacularly and leading it toward success. And now I'll turn it over to you, Barry. Thank you.
I want to spend my few minutes this morning paying tribute to LIGO itself and the LIGO team who built LIGO, operated it, upgraded it into advanced LIGO, and are responsible for the success of this fantastic instrument. It's very easy to be seduced and to be excited by the science that's come out of it, and we've heard that in the last talk, and I include myself in that. But we shouldn't overlook the fact that LIGO is probably one of the best and most amazing instruments ever built by mankind. 21 years ago, after we began the construction of LIGO, we finally struck gold, or black holes anyway. It's hard to imagine what we saw, for me, that we saw two compact objects, each of them only about as distant in size, big in size as the distance I drove this morning from where I live in Santa Monica to here, but weighing 10 million times as much as mass, having 10 million times what the Earth has. And the two objects may be separated from here to Santa Barbara, going around each other at half the speed of light, emitting gravitational waves, and we captured the last 0.2 of a second when they merged into each other. So it's so capturable and so fantastic, the science, it's sometimes easy to forget what it takes to do it. Since that time, we've actually reported a total of 3 more black hole mergers, and the details of those are giving us clues, at least, not results yet, on what are the ideas for example, what Kip mentioned, that is they're heavier than was predicted before we made the measurement. So how did we get here? About 30 years ago, Caltech and MIT formed a not typical, an actual intimate relationship with each other and a collaboration to first work on the R&D and then the design for this, much of it under Robbie Vogt, and then to construct it. And that collaboration is basically the LIGO lab that was referred to by Kip, and is responsible for building this instrument, operating it, improving it, and making these measurements. So that's what I want to talk about. LIGO's construction began in 1994. After Kip and I went to the National Science Board and testified, he did the science. I talked about how we would go about building it and what we needed to succeed. And the collaboration basically continued after that, funded by the NSF program, the major research equipment funding. One miracle in this whole thing is the NSF itself, and we have to pay tribute to the NSF. It's our science agency in the US, at least for physical sciences. And the NSF has as its priority and as its mission to do the best possible science. How else could they defend spending as much money as was spent on LIGO with no results for 20 years and keep defending it and getting it through Congress? It takes people at the top of the NSF to have that dedication, belief, and so forth. And you don't do great science without taking risks. So the NSF deserves a lot of our credit. LIGO was a huge extrapolation from anything that had been done previously. Prototypes were built. We still have one being modernized here on the Caltech campus, which was 40 meters in length. There was one in Germany that was 30 meters in length. We were extrapolating a factor of 100. Usually in physics, that's too much. People don't really believe you. We also extrapolated another maybe factor of 100 in sophistication in order to get the amount of improvement we would need to detect gravitational waves. This huge extrapolation, of course, made some people dubious, as we heard earlier, that we could ever succeed. But we did it in steps. We basically built what we called initial LIGO. With initial LIGO, we went through 6 different runs of the instrument, each one failing to detect gravitational waves, but at the same time understanding what limited us and then improving that for the next data run. We didn't get discouraged. We went through 6 different runs on initial LIGO and then moved to advanced LIGO, where we've had more success. And we've had 2 data runs now on advanced LIGO, improving the detector in between the 2 by the staff of the LIGO laboratory. So for me, LIGO and the Caltech MIT LIGO laboratory are the real stars of the story. Not just the instrument, but the people who have built and operate it. I had the privilege of serving as the director through the construction and the initial LIGO running, and the R&D and design of the advanced LIGO. Jay Marks, who's here somewhere, over here, who I'd like to stand for a minute so people can see him, took over as the director. He was the second director, and basically the effort that I described continued without losing a beat. Dave Wrightsey, over here, please stand, is the present director. Jay came, like I did, from particle physics, particle accelerators, a lot of experience with large devices. Dave Wrightsey came with experience in lasers and optics, which is the heart of LIGO, really. And he's participated in almost everything in LIGO, from the big 1,000-member collaboration, where he served as spokesperson, to being the present successful director, where we've made the detections. 2 other people that I'd like to mention, well, one that isn't here I'd like to mention first, which is Gary Sanders, who was the project manager, is what we called him, when I was running LIGO. And it was his ability to take academics, if you want, and provide enough discipline so that we could build this instrument. 2 other people have been at the center of almost everything that's been done. I'd like to name everybody in LIGO, but I can't. But I want to name 2 people. One is Stan Whitcomb. And Stan has been in the center of everything all the way, from the R&D to the construction, to when we started making it work. He was in the center of that, to the writing team that wrote our first paper. So it doesn't matter where you go in LIGO, wherever Stan is going to be the center of the activity. The other is Albert Lazzarini, who was one of the first and best hires I ever made. And he has participated as the deputy director for the last 2 directors, and has participated before that in doing even integration and engineering work, which is not what a physicist usually does, but he can do everything also. They represent only a few of the people in LIGO. There's a bunch in the audience. I'd like to ask everyone from LIGO to stand up so people can see them, because they're the real people here. finally, on a more personal note, I feel incredibly fortunate to have been part of LIGO and its successes. It's just amazing that this has happened to me as a person. But I would have never been able to do that without my continuing support from my family, who are all here today, from grandkids to my wife and my two kids and grandkids and my wife. And so with that, I'll quit. Thank you.
So thank you all. We can take a few questions now. If you can please identify yourself, the news outlet that you're with, and who your question is for. And we have some microphones here.
Thank you. Thank you for taking my question. My name is Kaori Ida. I'm with NHK Japanese Public Television. If I can ask both of you, can you remember for us what happened at 2:45 a.m. this morning? What were your initial thoughts? How did you get the phone call? Were you watching on webcast? And also, moving forward, do you have any dreams or ambitions since you have this Nobel Prize now? Thank you.
Answer first. You got the first call.
Okay. So my call came just before Barry's. Mine was at about 2:15. It was surprising how long they talked to each of us. I was sound asleep. And so the phone rang. I knew it was November 3rd. I knew it was the wee hours of the morning. I knew it had to be coming from Stockholm. I struggled out of bed and made my way to the phone, which was down a flight of stairs in my wife's office, and took the call. And I had thought, you know, we've been expecting this. I had hoped it would go to the team. It didn't. It went to us. But we had been expecting it, and so I thought, well, I'll be blasé, but in fact, I was overwhelmed. I don't know why.
So my call came after Kip's, but enough after so that I had already, we were warned this may happen, so we were ready, and not ready, but prepared. And so I had set the alarm for 2:40 a.m., knowing that 2:45 is when it was supposed to be live streamed. I got up at 2:40 from the alarm. There had been no phone call. So, so I assumed they had passed us over. Instead, I went to my laptop to try to see, well, who did they give it to or what? And then my cell phone started ringing. And whoever here can tell me how they got my cell phone number that I give to nobody, I don't know, or how they got anybody's number, but mine is a cell phone that I don't give out, so I don't. But they called on my cell phone and then was like, Kip. My feelings at the time, I think, were a mixture between, complicated mixture between being thrilled and being humbled. Yeah, I guess I'll answer that first. I think my role, Kip's role, Ray's role is to keep this going to the fantastic science that can happen in the future. And to do that, we need to really keep improving this instrument. So from my standpoint, the most important thing that can happen to make the science really open up is to make LIGO better and better and better, which takes creativity, money, unfortunately, and developments, and to actually figure out what happens after LIGO. What's the next telescope that we build or the next gravitational wave detector? And that's where I think the effort has to be.
In my case, as I said, I pulled out from day-to-day involvement with LIGO in the early 2000s, and this really is the triumph of the team that you see here, not my triumph. I stand on the sidelines and cheer them on, but I also am really moved by the vision of what's going to be done over the coming decades, particularly exploring the birth of the universe, which will first come from a different technique, cosmic microwave background simulations, which is pioneered here at Caltech by Jamie Bach and before him, and by the team around him. So the idea that you'll explore the birth of the universe, explore the birth of the fundamental forces, in this case with LISA, the space-based detector, these are dreams that have been part and parcel of my evangelizing going back several decades, and they are dreams that I still hold to myself, near and dear to myself. In terms of my own time, I'm in a phase of my career where I have chosen to do science communication to the general public by means of collaborations with filmmakers, with artists, and with musicians. My Hollywood partner, Linda Obst, is here on this occasion, and we are working together in that direction. And I just find it a great joy to be able to work with creative people in the arts to try to communicate these wonderful ideas about science, technology, and the universe.
I'm going to repeat a question that was asked in Sweden to Rainer this morning.
Can you introduce yourself?
I'm Deepan. I'm a graduate student. I shouldn't be sitting here. So 100 years ago, in 1914, Röntgen got the Nobel Prize for his discovery of X-rays, and he didn't know what X-rays would be used for 100 years later. To Kip and what do you think 100 years from now? Gravitational waves beyond the direct implications of understanding the birth of the universe. Do you think there's other realms of science that gravitational waves could touch?
You want to do that?
Okay, I'll give an answer, and then you can. I think that the technology for generating gravitational waves is so difficult, so much more difficult than detecting the waves, that I'm dubious that we can expect within 100 years to be generating them, detecting them, and using them for human technology. I could be wrong. I've been wrong many times in the past, but I see this as far, far more challenging than what has been achieved.
Yeah, I don't think any of us can envision, well, of course, general relativity, you didn't envision using that for anything, but we all use it for GPS every day. But for us, I think you can ask what fundamental science, maybe beyond the early universe, you might do. I have my own dream what that might be, and that is coming from two fields. We have two theories of physics, really. Quantum field theory that does physics at very short distances, and this Einstein's theory of general relativity at long distances, and never the twain shall meet, kind of, although people try to work on that. And I think the one thing that's missing is that we only have theoretical ideas how to pull that together. And maybe someday we can study gravity where it's most important, really around black holes, which is the laboratory that we opened. And also it has quantum effects that maybe we can find some clues experimentally to pull this together, because as long as we have two completely different theories, very successful, both of them, of physics, we're not there yet.
Hi, Calla Cofield with Space.com. You mentioned in your speeches a bit about the risk that the NSF had to take on LIGO, and that many people who participated were taking as well with their careers. Can you talk a bit about lessons that you take away when taking a big risk like that in science, both for the individuals involved, but also in the current funding climate and going forward with major projects, with other projects that would require a lot of risk? What have you learned? What would you advise?
I think you're best to take that, Barry.
Yeah, let me do the human part last, because that's the hardest part always. I think what's fundamental is you have to be willing to take risks to do great things. It's just, there aren't very many things you can do that don't have risks involved. And the question always is, how do you maintain a system where you can pick the right risks to do and to achieve those? For science, it's pretty good. We know what we want to do, get the best possible science. So then you can ask how much risk it takes to ask that kind of scientific question and try to decide between those. And I think the purity of a real science agency like the NSF, if it works right, can do that. The problem now is twofold. That is, how well does the NSF work compared to how well it could work? It has to be accountable to the US government. And the accountability to the US government makes it really hard to defend taking risks. so that the accountability is much worse now than when we started LIGO. So I don't know if the equivalent risks could be taken by the NSF very easily now and defended in the government. It's a real problem. Then on a more individual level, the NSF uses peer review to decide which projects, which even a small lab, which things they should fund, which things they shouldn't fund. And that's done by you submitting a proposal. And if you get all excellence, then you get funded. When you have too many proposals compared to the number you can fund, then the only ones you fund are the ones that score all excellent, say. And that means you've picked the ones that are the least controversial, the least risky, and so forth and so on. So it's a constant struggle to try in our system to take risks, I think. It isn't that we take too many. We don't have that many failed projects. It's that we really don't have a good mechanism to take on risks and defend that. And I think the more risks would be better.
Let me just add one thing, that the ability to take risks that resulted in LIGO had a lot to do with two individuals who were at NSF in the 1970s, 80s, 90s, Richard Isaacson and his boss Marcel Bardon. And they shared the vision we had, and they knew how to communicate with the rest of NSF and to communicate the value of this science and the fact that it was going to take a long time and be very hard. And so success really depends on people like that in government as well, who have the vision, share it, and know how to communicate it, as well as people on the ground in LIGO.
Yeah, I think that in particle physics, which I came from, actually does it pretty well. And that is that there's a lot of people, they seem faceless to the outside world in these big collaborations. But inside, everybody knows who does well and who does good things. And people who do good work inside of a major big collaboration, which looks faceless, emerge, and it just seems to work no matter what. I think LIGO is following the same pattern. Many of the people that started and were young during the time when I was running LIGO have gotten first-rate jobs, and they're the ones that I would pick today. So the quality emerges out of these big projects mostly because scientists recognize their colleagues that are good. It's easy to do that, and the system works very well. It doesn't have to be that somebody published a paper himself that has a lot of citations or something to move on in this kind of science where there's more individuals and groups involved.
Do we have any questions online?
This is a question from Seth Borenstein of the Associated Press. Ray Weiss said comparing gravitational waves to sound or music may not be quite right, but others have called it the music of the universe. Is it like music, even though it is not a sound wave? And if so, how would you describe the music that you hear? Is it classical, jazz, rock, etc.? How beautiful or not is the music that we now can hear, and how important is it that we hear it?
So, well, let's take the first detection, the famous chirp. It was a chirp. There was a beautiful New Yorker cartoon. The very next day, two birds sitting on a branch. One of them says to the other, was that I heard just now, was that you I heard just now, or was it two black holes colliding? And so, yeah, it looks simple at first. But then when you go in, as the LIGO team has done, and you look in detail at the detailed shapes of the waves, you discover there's a lot of information there. And the beauty of the signal, the beauty of the symphony is in what you can extract from the tiny wiggles or the wiggles on tops of wiggles in that signal. The beauty is that science thing that comes out, in this case, insights into the storm in the fabric of space-time that produced it.
Hi, John Schreiber with CBS2. One of you said this is quite possibly one of the greatest things ever made by man. I'm hoping you could expand on that for somebody like me who didn't do too well in physics. What makes it so great? Just try to break it down for somebody who has no understanding of physics.
I suppose that was me. Everywhere you look in LIGO, we've pushed technology, almost everywhere, we've pushed technology to its limit. The whole system has to be in vacuum. A lot of experiments have to be in vacuum, but the vacuum we have is what we call high vacuum. And there's a larger volume of vacuum than any instrument in the world except the big collider at CERN. So there's only one, and that's just one of our facilities. The lasers themselves are very, very specialized. The optics is beyond the state of the art that we use, and we have to develop our own optics and coatings and so forth to move on because nobody knows how to do them at the level that we need. So almost everywhere you look in LIGO, certainly the seismic isolation, which was key to making the discovery, is well beyond what people can do otherwise, how well we isolate ourselves from the Earth. So everywhere you look in LIGO, we've pushed technology to the limit. On the other hand, I would say that LIGO and other big science has benefited tremendously by the advances of technology. So we advance technology and that feeds down into society, but it happens the other way around. LIGO couldn't have been done 30 years ago. We didn't have lasers like we have today. We didn't have optics like we have today, and so forth. We didn't have digital controls like we have now. So everywhere you look, basically, we're able to do complicated, modern, important science now that we couldn't do before. And part of that opportunity is in really doing these large, complex projects. I like to point out that 3 of the most important discoveries since the new millennium, since 2000, all involve very high-tech, large collaborations and complicated devices. Ours is the 3rd one. The other 2 are the neutrino experiments underground that recently won the Nobel Prize for the neutrino mass. And the other is the discovery of the Higgs boson at CERN in these most complicated devices that were built at CERN. These are built by large international collaborations, even bigger than ours, and using the most modern technology, electronics and so forth, some of it developed inside and some of it because society has advanced.
All right, maybe one more question if there is. Yes, please.
I'm just curious, like, what the biggest... What? Your name? Oh, I'm so sorry. Thank you. Deborah Nethburn from Los Angeles Times. I'm curious what some of the biggest hurdles were to getting here. Were there funding? I mean, was there ever times where it felt like the project wasn't going to go through because of funding, or that the technology just wasn't there? What were the challenges?
Let me make just brief remarks, and then Barry is in a better position to talk about the technical side of things. But I think one remark that I would make is that in terms of funding, that once NSF had put in the first funding, this project was backed at approximately the level of funding that we requested and needed continually from then in 1992 until today, and backed not just by NSF, but by Congress as well. By Congress, whether it was Republicans in power or the Democrats in power. So it was really remarkable that the stumbling blocks, once we got the first funding, were not the funding. Now, getting the first funding was a hell of a thing to do, and it was Robbie's achievement to get that very first funding. For me, I mentioned a huge stumbling block was the problem of being able to simulate the sources. This is done outside the LIGO project, and it illustrates the fact that to make everything come together, you need more than just what went on within LIGO. There were technical difficulties that people just didn't know how to deal with, and turned out they were resulting because the physicists did not understand the mathematics of Einstein's relativity well enough. And it was only after they started talking to the mathematicians that they really realized where the problems were and sorted this out. And that, again, illustrates that skills from very different areas really have to come together to make this happen. I'll let you go to the technical side of things, Barry.
Yeah, I think things just took a long time. There were minor setbacks. I don't think we ever had a major setback. We basically have done this in steps and learned how to do it as we went along. It's the first time people have done this kind of thing on this scale. And I talked about the fact that we ran 6 times, and each time we learned, which we couldn't know in advance, what limited us and improved things. Some by design, we knew in steps we were going to do things, but probably the amount of time that it took to get to where we are today is twice what I thought it would be. But that's often true when you do hard things.
All right. Thank you all very much for coming. I think we'll go ahead and wrap up the press conference portion today. Our speakers will be around for a short while after we finish to answer any other questions that you may have. And please join me in thanking them and our Nobel laureates one more time.